All right, everybody, 4 o'clock. Welcome back to your favorite class. Yes. Okay. Announcements. Really, the only announcement right now is that your homework 2 has been posted. That's on micromechanical models, kind of the stuff we've been doing right now. And that will be due on Tuesday of next week. And after today's lecture, you should be able to do it all. All right. So we're kind of done with the continuous fiber micromechanical models after today. We'll kind of put a bow on help and sci and do an example problem. And that'll kind of be it for micromechanical models. So that's that. Right. So let us then do the lecture things where we do the things with the lectures. Okay. So let's recap kind of where we were with our micromechanical models. And specifically, again, just to remind you, this is for continuous fibers. I kind of sort of dropped that connotation over the last couple of lectures, but I just want to make sure that you know that what we're talking about now is for continuous fibers. I think that's kind of inherent in what we've been talking about so far, but I'll just make this clear. All right. We have the rule of mixtures, which is called the parallel model, which is property of the composite is property of the matrix, volume fraction of the matrix, plus property of the fiber, volume fraction of the fiber. And this is good for kind of two quantities, modulus in the one direction and Poisson's ratio 1:2. It's really the only model. This model is only really good for those two properties. All right. Then we had inverse rule of mixtures. Okay, this is the series model. Whoa. Oh my gosh, everything is blowing up. Ah! Uno momento, por favor. Why are you angry?
The screen for like sharing keeps flickering every few seconds.
Sorry, it's just kind of blew up on me. I don't know what's going on here.
Yeah, I could see from the projector in the background. I just figured I'd mention it.
All right, let's try this. Okay, we're back. Sorry about that technical difficulty. Okay. So the inverse rule of mixtures, the series model, and that is 1 over property of the composite is volume fraction of the matrix over volume fraction, or sorry, property of the matrix, plus volume fraction of fiber over property of the fiber. And I'll say this is good for G12. And it is sometimes used for the modulus in the 2 direction, but I'll say only okay. Got no other way to really say that except it's suspicious. Okay. And that's because it's only okay mostly because of stress concentrations. So remember our model, we sort of assumed that we had load in the 2 direction, and we neglected the stress concentration of the fiber for that particular model. So inverse rule of mixtures, you know, a little suspicious, let's just say. All right, so those are your 2 mechanics of materials models. And then the final model that we talked about was the combined parallel and series model, which we also call the help and psi model. Or more colloquially known as help and psi model. All right, and we went through some derivation there with a little bit of nonsense. There's some sort of flavors of your electrical engineering classes, circuits classes, where you're talking about parallel and series. flow of electricity. This is kind of a similar idea where we have parallel and series like flows of stresses inside of our composite. And the idea here is the general equation is going to be the property of your composite is the property of the matrix times this sort of strange looking 1 plus xi eta VF over 1 minus eta VF, where this eta and the xi are stand-ins for some semi-empirical values that we would get from experiment. Okay, so here's your help and psi model, and let's just be clear about what the xi and eta are. So xi is an empirical value from experiment. Right? And eta is a combination of the properties of your individual constituents and the value of psi in that equation above. So eta here is property of the fiber over property of the matrix minus 1 divided by property of the fiber divided by property of the matrix plus psi. Right. So there's your equation for eta. We sort of graphed the upper and lower limits of the composite properties by looking at sort of the extreme values of xi. So let's do that quickly as a reminder. This is about where we left off last time. We looked at what the properties of these composites would be as a function of volume fraction of fibers. And as your volume fraction of fibers approaches 0, you're going to approach, obviously, the property of the matrix, whatever property you're talking about. All right, so here are your properties. And as the volume fraction approaches 1 or 100% fiber, you're going to approach the property of the fiber. Okay, so usually that is greater than the property of the matrix, typically. So that's why I sort of draw it, quote unquote, above on the y-axis. And we looked at the rule of mixtures and inverse rule of mixtures models and saw that the parallel, which is the rule of mixtures, is this linear line between PM and PF. So this is rule of mixtures. And in this situation, for rule of mixtures, the value of psi is infinity. We also looked at the inverse rule of mixtures, and that's sort of this like 1 on x looking function. Inverse rule of mixtures. And this sort of represents the lower bound on the properties that you could have for your composite. And in this situation, xi is 0. All right. You will show on your homework that when xi is 0, you converge to the inverse rule of mixtures, and you will show that when xi approaches infinity, you converge to the rule of mixtures. All right, that's your first homework problem. If you have problems with that, see Jack Tarasak, he's finished it. No, I'm just kidding. Come to my office hours. All right, so depending on which particular property of the composite you're interested in, there are generally accepted values for psi. Right? So generally accepted values all right. 2 of these you kind of already know. If you're trying to calculate the modulus in the one direction, you more or less want to use the parallel model, which would mean that we would say that xi is what value? What value of xi for the parallel model? Not everybody at once. Infinity.
Infinity.
Okay. So xi equals 0. I drew 0. The opposite of 0. Infinity. Same idea for new 1, 2. We are going to use the rule of mixtures to calculate new 1, 2. Now, the other 2 are a little bit more subtle. I would say these are well established. No issues. What is that song about? I got issues, and one of them is how much I miss you. Yeah. That's how I feel about this class when I'm not teaching it. All right. E2, a generally accepted value, is xi is equal to 2. And G12, a generally accepted value, xi is equal to 1. Now you see these are much closer to 0. Okay, so we're approaching the inverse rule of mixtures, right? But not quite there, all right? So this is, I'll say, better than inverse rule of mixtures. But still lots of variance. Okay? So what do I mean by that? Okay, well, you might make a composite and predict what the elastic modulus in the 2 direction is using a value of psi equal to 2. But then you take that composite to your lab, because you all got a lab at home, and put it in your load frame, because you all got a load frame at home, and do an experiment where you're testing what are the actual moduli values in the 2 direction. And you might plot all this data and find out, oh, a psi value of 4 is more appropriate. Okay? That's kind of the way that the world works with this particular equation. It's semi-empirical, and so people make estimates based on a value of psi equal to 2 for the modulus in the 2 direction, but in actuality, it's a little suspicious to just generally assume that. Assuming infinity for E1 and nu1 is pretty solid, but these guys here, a little suspicious, okay? So we'll just say that. All right. Onwards, an example. Finally, enough talky. Let's do an example. All right, I'm going to pop this up for all to see. We got a unidirectional carbon epoxy composite with the following constituent properties. We know the modulus in the 2 direction of the fiber. We know the modulus of the matrix. We know the Poisson's ratio of the matrix, and we know the volume fraction in the composite is 65%. We want to determine the transverse modulus, this E2 value of the composite, using the 2 approaches we talked about. So I'll give you a second with that. Trying to think about what I could wax idiotic about for the next minute while you copy this down. How about register to vote? There you go. That's not waxing idiotic. That's waxing intelligent. Okay. Register to vote. Dang it. Wisconsin's an important state, and you're an important vote. Not telling you who to vote for. I'm just telling you to vote. If they're all idiots, then, you know, pick the best idiot. Okay, so let me ask, you guys can keep copying down, but which mechanics of materials model are we going to use for E2? Which one is more appropriate? Rule of mixtures or inverse rule of mixtures? Inverse rule of mixtures. Good. Okay. I'll copy the relevant information down here, so if you're still working, keep going. I'll get down the important bits, okay? So we've got a carbon fiber epoxy composite that's unidirectional. So let's just draw a picture so we're all kind of on the same page on what's happening. So here's your unidirectional composite material. And we got fibers more or less like running in this piece all this direction. All right, this is a unidirectional composite, sort of all the fibers running in the same direction. Remember that when we have this unidirectional composite, our one direction always in the direction of the fibers. So here we go. 1, 2, 3, the coordinate system we're going to use here. And we're asked to predict E2 using first the mechanics of material model. And we mentioned here that we're going to use the inverse rule of mixtures. And we're going to use predict the modulus using Halpin psi. With xi equal to 1. So when we're predicting E2, what we're predicting is, sort of the modulus in this like 2 direction, sort of across the fibers themselves, okay? All right, we're given information about the constituents. So we're told that the modulus of the fibers in the 2 direction, remember that fibers themselves are anisotropic. Carbon fibers have a different modulus in the 1 direction than they do across the individual fibers themselves. This is 14.8 GPa. The modulus of the matrix, 3.45 GPa. Maybe some of you have that GPA. 3.45 GPA for the modulus of the epoxy. The Poisson's ratio of the matrix we're given as 0.36. Remember, this is Poisson's ratio. I'm trying to do my best to sort of like make the script here so you can sort of distinguish the lowercase. This is actually the Greek variable nu. And then capital V F, this is the volume fraction. This is the amount of fibers that's in the composite, 65%, or 0.65. All right. If we assume a solid composite without any voids, what does that mean that my matrix volume fraction is? If I have 65% fibers, how much matrix do I have percentage? 35. So that you can maybe just write straight away. Don't confuse Poisson's ratio nu sub m with volume fraction capital V sub m, all right? All right, so away we go. First is our inverse rule of mixtures. Okay, this is just kind of plug and chug, all right? So we know it's 1 over the property of the composite that we want. So here that's 1 on E2. That's the property that we want. Equal to volume fraction of the fibers divided by property of the fiber of interest. So that's EF2 plus volume fraction of the matrix divided by property of the matrix. This would be EM2, but since the matrix is isotropic, we just write EM. The matrix does not have any directionality associated with its modulus, okay? So we just write it as EM. All right. You may often see this solved in this general fashion. I'll put this as E2 and maybe I'll give it a MOM because you all love your mothers. I'm going to write this as volume fraction fibers 0.65 divided by modulus of the fibers in the 2 direction. It's 14.8 GPa plus volume fraction of the matrix. We said that's the 1 minus the volume fraction of the fibers, all divided by the modulus of the matrix. It's 3.45. And I'm going to write all of this inverted. So you sometimes see it in this form. I just wanted to show it once in this general form. Hopefully we can all kind of understand that methodology. Be careful not to just simply invert these terms. Okay, that's not accurate. Okay, I'm going to invert that whole right-hand side. All right, so you punch this into your calculator. Those magical, mystical, amazing things that you carry around. 6.88 GPa.
Dr. Hart.
That's your mechanics of materials method, strictly using the inverse rule of mixtures. All right. We can also use our second model that we talked about, this kind of combined parallel series model, which we know is the Halpin Psi equation.
Dr. Hart, can I ask a question?
It's kind of our other model. General form is going to be the modulus in the 2 direction. This is our modulus of the composite in the 2, is the modulus of the matrix times 1 plus xi eta vf on 1 minus eta vf. And so we're going to have to figure out eta and sort of define xi. Xi is given to us in the problem. We're told to assume xi is 1. Okay. This will then help us calculate eta, which the general formula, property of the fiber divided by property of the matrix, minus 1, divided by property of the fiber, property of the matrix, plus xi. Okay, so the property of interest here is the modulus in the 2 direction. I'm going to drop the GPA and just put the numbers here. 14.8 on 3.45. This is the quantity. I'll just be clear about that this is a quantity, minus 1. All over the quantity, I guess it's maybe a little unclear from how I wrote it before. 14.8 divided by 3.45 plus xi, which is 1. So you'll end up with an eta value here. Oh, that's actually a really good eta. Dang, that's like the perfect eta. I've never written a perfect letter before ever in my life. My handwriting's horrible. So this is like the most amazing. Look at the little curly on the bottom there. Dang, let's go. It's the best eta I've ever made my whole life. All right. Eta here, 0.622. Dang, I want a picture of that thing. Okay. I'll sign my name right here. When you're a doctor, that's how you sign your name, okay? All right. So now all this goes back into our original equation. All right. So here we go. We're ready. Modulus of the matrix, 3.45 GPA. You all wish. 1 plus what is 1 times 0.622 times the volume fraction of the fibers, 0.65. This is all on 1 minus eta 0.622 times volume fraction 0.65. Sounds like Matt Rogers is furiously checking my work, which is nice. Always nice to have someone in the background catching your mistakes. Good luck. So I'll write E2 subscript Halpin Psi, 8.13 GPA. How'd I do, Matt? Okay, he's giving me the thumbs up. All right. Now we're also asked, kind of one additional piece of information. We're asked if the actual value of the modulus is 8.02 GPA. What's the error in each one of these? All right. So if the actual is 8.02, what's the error in each of these? General formula is going to be, I'll use kind of the script E for error. I think that's kind of commonplace. It's going to be the absolute value of your calculated minus the accepted over the accepted. So this will be 6.88 GPA minus 8.02 GPA, absolute value here, all over the accepted. Jeez. 8.02 GPA. This will give me error for the mechanics of materials model, which is going to be 14.2%. Similar calculation for help and psi, except we're going to use 8.13 minus 8.02 all over accepted value of 8.02. And you'll end here with 1.4% error. All right. These are probably pretty accurate to what the error would be. Sort of, again, just kind of depends. It really depends on the composite that you end up making. All right. Any questions on this from the Galleria of Jewelry or the audience? What's the gallery? Which one is the Galleria of Jewelry? Is that Jared's? Or is that K? Or is that Kessler's? Oh man, they're all like the same. Aren't they like all owned by the same guy? I think they really are, actually. No one in the chat knows either. Oh. All right, someone's asking something. Oh, darn it. Vote. My GPA is closer to Poisson's ratio. Yeah, I don't know what happens there. Someone asked something? Oh, I didn't hear.
Hello.
Oh, there we go. My headphones were on mute. Sorry about that. Okay, ask away.
So this question was from a while ago.
Okay,
but
sorry about that, Lucas.
I just was wondering if you could explain why you went with the inverse rule over just the regular one.
So the question is, why do you go with inverse rule over the standard rule of mixtures? Well, over many years of, sort of experimenting with composites, people have found that the generally accepted value of xi for calculating the modulus in the 2 direction is around 2. And since the inverse rule of mixtures would have a xi value of 0, and the rule of mixtures would have a xi value of infinity, the value of 2 is much, much closer to the value of 0 than it is to infinity. So because of that, people go with the inverse rule of mixtures because it's more representative of actual practice.
And is that like just kind of a universal rule?
So Lucas asks, is that a universal rule? I would say most people will use Halp and psi equation with xi equal to 2 to predict their composite properties. But if they really must know, they will do lots of experiments to determine the actual value. Is that clear?
Yep, thank you.
Okay, sorry that I missed your chat. My volume was like all the way down low. I got like this little volume knob on here. Sometimes the wheel goes all the way down, which is, annoying.
That's all right.
Sorry about that. Okay. Other questions? Okay. Then that would conclude our micromechanical models for continuous fibers. And we now move on to micromechanical models for other types of reinforcement, including short fibers and particulates. All right, so let us move on to micromechanical models for short fiber composites. All right. So kind of back at the beginning when we were talking about materials, we sort of had a loose definition for short fiber, and that was that the aspect ratio was somewhere between like 3 and 500. Okay, so let's remind ourselves. Short fiber composite. Okay, has reinforcement with aspect ratio of, I'll say, approximately 3 to 500. Remember, aspect ratio is like the ratio of length to diameter. So if you need that clarity, length over diameter. Okay. So your continuous fiber composites, usually, your reinforcement is meters or longer in length, and your diameter is micrometers. So obviously that's an aspect ratio of closer to 1,000,000, etc. Okay, so that's what we would consider a continuous fiber composite. 500 or more, right? Now, our short fiber composites, depending on how they're manufactured, you can have some sort of alignment of the fibers or not. And the models that we have kind of depend on whether the fibers are aligned in the piece or not, like for pretty obvious reasons, okay? If you're doing an injection molding process, and that injection molding process leads to a situation where all the fibers that you're injecting happen to be oriented in one direction, well, the composite's going to be much stronger and stiffer along that direction, think like rule of mixtures, than it is across that direction, think inverse rule of mixtures, okay? So we need micromechanical models that can accommodate sort of aligned or partially aligned or completely random orientation of short fibers, all right? So let's be clear about that. Okay, so for a good model, we need to include the following information. Obviously, properties of the fiber in the matrix gonna be important. All right. What else is important? Volume fraction. Okay. When we're talking about short fibers, now we should probably include in our model the aspect ratio, because the aspect ratio will be important. If you have many, many long fibers, that's going to kind of approach the models that we use for continuous fibers. And if you have very, very short fibers in your composite, that's going to approach kind of like a particulate model. All right. So we have to sort of include our aspect ratio or something like the aspect ratio in our model. Right. I sort of just mentioned this, but we need to accommodate the distribution type. All right. Is it aligned, partially aligned, or random? All right. So alignment of fibers. And I'll kind of like draw some pictures over here to kind of show exactly what I mean. All right, if we think of like aligned short fibers, we're just kind of like looking head on at a particular composite. Well, that might be something that looks like this, where they're all sort of like aligned in a particular direction. Like so. You may have partial alignment. So this is partially aligned, where, yeah, they're kind of like aligned in a bit of a direction, but there's a little bit of randomness to it, okay? I think you can say maybe that those guys are sort of trying to be up and down, but it ain't quite so, right? Or you could have completely random, which frankly, ridiculous. Okay, you get the idea. Random nonsense. All right. The last thing you want to include in your model, and this is something we'll discuss, is obviously the orientation of the fibers with respect to the load. Okay, we know that if we're pulling in, let's say, the alignment direction of the fibers, we're going to have different response than if we pull in the, across the alignment direction. Okay, so maybe up here, alignment of fibers in composite. If aligned or partially aligned. All right. I should maybe say that these models are actually quite complicated. So when you're talking about including short fibers into a matrix, there are certain limitations and certain mechanical responses at like the ends of the fibers that are rather complicated. Okay, so in the middle of a long fiber, you can hold tension and compression relatively easy inside of a composite. At the ends of the fiber, you don't really hold any normal stress because you don't have your fiber to hold normal stress. Okay, so the models are much more complicated. All right, so instead of diving in on these short fiber models for what could be a really long time, I'm just going to kind of talk about the methodology behind the derivation, and then we'll just kind of present the solution. So I'll give you enough information where you're kind of learning about why the models are so complicated and what's like really happening, but gonna kind of jump to the final result without all the algebra and actual derivation. Okay, so let's make that known. Models are quite complicated. Okay, so I'll say we'll present general ideas, but omit full derivation. Okay, you want the full derivation of short fiber composite model? Go to graduate school and write a research paper. I don't know what to tell you. Complicated. Actually, it's in your book. Like if you really want to dive in, you could go in your book and dive in on it. Okay. The first one we're going to talk about it is the aligned short fiber model. And that's because that's actually like pretty closely related to the continuous fiber model. So first one we'll talk about. All right. The picture you should have in your head again is like something like this, where all of your fibers are, running in this direction, or very nearly all of them running in that direction. And this has some natural coordinate system to it, where 1 is the direction of the fibers, 2, 3, right? So we're going to assume that sort of coordinate system. And this is going to end up looking a lot like the micromechanical models we previously saw. And so we're going to leverage for this help and psi equation. And just a reminder, that equation is like, if you're looking down like the one direction, well, let's just do it in terms of the property of the composite. That's property of composite is property matrix 1 plus xi eta vf. That eta was much worse. On 1 minus eta vf. And for this short fiber model, we're aligned with these tiny short fibers. And we know in this help and psi equation, our wiggle room really lies with that variable xi. Okay? Now, we're kind of aligned, and we want to kind of pick a xi value that at least is representative or has some relation to the aspect ratio. And we would like the aspect ratio, when it approaches infinity, to be representative of what is the parallel model for E1 and the series model for E2. Okay? So what we'd like to have is such that it uses the aspect ratio. So that, for instance, for E1 as aspect ratio goes to infinity, that xi should also go to infinity, right? Because that is the parallel model, which is normally what we'd use if we had continuous fibers and we're trying to calculate E1. So the way that this is generally accepted, and people just kind of have done a lot of experiments to prove this, is that for E1, we'll say that xi is equal to 2 times the length of the fiber divided by the diameter of the fiber, where L is the average length of the reinforcement, and D is the diameter of the reinforcement. Okay? You know, L over D is your aspect ratio. Okay? All right. Now, if you're looking at calculating E2, the response of a continuous fiber composite versus the response of a short fiber composite is really going to be governed by concentrations of stress around the fiber. Okay? So let's make a note of that. Response of continuous fiber composite and short fiber composite when loaded in 2 direction is similar. And that's because it's mostly governed by stress concentration. Okay, can I get this over a little bit? Stress concentration.
What does that say? It says it says 2 direction. It looks like a
Is similar.
like a B. Oh, is similar.
Sorry. Short fiber composite when loaded in 2 direction is similar. So what do I mean by that, like pictorially? Well, if you've got a continuous fiber composite, you've got this sort of action going on. Looking at it from the side. Okay, here you are loading in this general direction. Right, this would be like loading in the 2 direction. Okay. Continuous fiber.
And that other sense is mostly
Governed by stress concentration.
okay.
Short fiber will look very similar. Okay, so if you're aligned, it's still going to look like this. And if you look at the cross-section, it is also going to look more or less the same as what you see for continuous fiber. Okay, so because of that, aligned short fiber composites use the same help and psi equation when calculating modulus in the 2 direction. It's the same as continuous fiber. Okay. We'll stop here today. I think it's naturally good stopping point, and pick this up on Monday. Reminder, homework number 2 you should be able to do. It's all on continuous fiber models. Take a stab at it. If you got questions, I'm in my office, quote unquote, on Teams every day, 8 a.m. to 9:30 a.m. That's it. Goodbye.
If I have a question later on at night, because I work during the day, can I ask you questions after that?
Yeah, that's fine. Just,
Okay.
You can email me, or we can set up a office hours appointment.
Okay, thank you.
Someone signed into this as Mr. T. I pity the fool who comes as Mr. T.